This is a short video about electric potential energies. What I'm going to do is I'm going to start off by having a constant electric field, and I'm going to ask what is the electric potential energy of a particle in this electric field. So let's set up a constant electric field. This could be something like inside a parallel plate capacitor where you actually have the electric field just being constant. So it has the same value, it's in just a homogeneous electric field, very nicely behaved. Let's put some charged particle in here. Let's give this a charge of Q, okay? And then of course you know that the force on that particle of charge Q given by the electric field, the force is just Q multiplied by the electric field vector. So in other words, the force is in exactly the same direction as the electric field vector if Q is positive. Of course, if Q is a negatively charged particle, then you find that these two things are anti-parallel and the force will be on this particle going in the other direction. And this is something that's going to come up in just a second. But of course, what we can do is we can ask, well, what's the work that the electric field does on this particle? So hopefully you recall that the work is just the dot product of the force with the change in position of that particle. So let's label S, delta S, the change in position of the particle. Say it moves from here to here, then that delta S is going to be that distance there. So force, so the work is equal to the dot product of force with delta S. But of course, as I've mentioned previously, F is in exactly either the same direction as the electric field or in the complete opposite direction of the electric field. So in other words, I can write out this dot product. I can write that this is the magnitude of the force, not a vector anymore, but just the magnitude. I could put magnitude signs on it, but I'm a little bit lazy. It's the magnitude of the force multiplied by the magnitude of delta S, multiplied by the angle between these two things, which of course is, or the cosine of the angle between these two things, and the cosine of the angle between these, or the angle between them is 0 degrees, therefore the cosine of 0 degrees is 1, and I simply end up with this being F delta S. Okay, well, we know what F is. F is just given by the value of the charge multiplied by the electric field. Again, I've just taken the absolute value of this, so this is just the value of the electric field. And so this thing ends up being Q times E times S initial minus Q times E times S final, where of course S initial is the initial starting point, S final is just the final position of this particle after it's moved. So this is an expression now for the work that the electric field has done on this particle. I don't want to know about the work, I want to know about the electric potential energy. Okay, and hopefully you recall that the change of the electric potential energy, so we'll label the electric potential energy just with a U. We could put a subscript elec on it or something along those lines, but we don't need to because we don't have any other U's in the problem at the moment. So we remember that this delta U, which is just of course equal to U final minus U initial, okay, U final minus U initial, this is equal to the negative of the work. So this is equal to minus W, and of course, minus W, we've just written out what the work is. Minus W is just Q, E, minus sign. So this one becomes a minus, and we just flip these two around. S, F minus Q, E, S, I. Okay? Now, I can match up these terms, and you can see that the final potential energy is equal to Q, E, S, the final position, just like the initial potential energy is equal to Q, E, initial position. So in other words, I can just write out that the potential energy, U, is just equal to Q times E times S. Okay, where now I've just dropped my subscripts, and this is quite a simple expression. Of course, just in the case of gravitational potential energy, I've actually made a choice here, and I've decided that I'm going to have a 0 point somewhere, and but in general, I don't have to do that. So what I can do is I can have just some arbitrary U naught, where of course we often choose, just like gravitational potential energy, we choose that potential energy to be 0 at some given point, which knocks out the U naught, but we don't have to do that. There is no real good reason to do that. But so this is a general expression for electric potential energy of a charged particle sitting inside an electric field. We could, of course, use this now to calculate using conservation of energy, for example. We could use this to calculate the motion of this particle in the electric field.